Okay, we content lah. Last lesson we focused on dot and cross. Now I hope you all still remember how to draw dot and cross diagrams, because we're still going to be continuing that today. Now take note, today we're going to touch on the first thing, which is called VSEPR theory. This is an expansion, right, of dot and cross diagrams. So we are going to expand on what we drew last week and incorporate more ideas into it. So you can turn over to page 29 first. We're just going to go straight into the theory. And immediately, right, you'll be greeted with two things. This right here is the definition of VSEPR. I'm going to copy out the entire thing as well, because there are some words over here that I need you all to highlight. Okay, number one, the electron pairs will arrange themselves around a central atom. Okay, around a central atom, as far apart as possible to minimize mutual repulsion. Okay, very, very lengthy sentence, but you need to memorize this, okay, for any time they ask you guys to repeat the VSEPR theory in the exam. Okay? Now let's just see what this is about first. Okay, the first thing I need you all to highlight, right, is the word electron pairs. Electron pairs is an umbrella term which encompasses both lone pairs and bond pairs. Now I'm sure you all know what bond pairs are. Bond pairs are literally just bonds, right? But lone pairs are whatever they are, not bonds. So electrons that do not bond at all, they are just extra electrons, those are your lone pairs. So I repeat again, bond pairs are involved in bonding, lone pairs are not involved in bonding. That's the only difference between the two. We're just going to call them electron pairs in general. Now guys, the next thing is, right, we are looking at the central atom today. Okay, focus is on the central atom. And guys, why do they want to be as far apart as they can? Because as we know, electrons do not like each other. Okay, if they don't like each other, right, they want to be as far apart to minimize mutual repulsion so that you can get as stable of a compound as possible. Make sense first? Okay, so that was quite self-explanatory. You don't need to really memorize it because it is quite logical. The second thing is this. The strength of the repulsions, which is still part of the definition, by the way, is as such. The strongest repulsions is lone pair, followed by lone pair, followed by bond pair. Okay, there's a lot of things going on here. LP stands for lone pair. Bond pair is your PP. So they never really explained much there. Okay, but I'll give you guys a little bit more insight into this so you all can remember a bit closely. Anyways, you put a lone pair and a lone pair together, it repels the most. You put a bond pair and bond pair together, the repulsions are the least. Okay, why? You don't need to know why, it's not your syllabus. But I think it's good to understand also. Now, lone pairs. I'm going to draw an example of HF. Now, as you can see here, okay, remember, a covalent bond is formed via what? How are covalent bonds formed? Okay, they share with electrons, but how do they share? Covalent bonds are formed via, what's this? Overlapping of orbitals, right? Okay, so remember, okay, let's just draw a little overlap over here. This overlap is basically your bond pair. We have drawn these diagrams in the previous couple of lessons. So in this bond pair here, I also want to talk about the lone pair. Now, which atom here has the lone pair, H or F? F has like 7 valence, right? Only one of it is used in bonding. The other 3 are basically lone pairs. Can I ask you all who is closer to the nucleus? Bond pair or lone pair? Okay, bond pair or lone pair? Which one is closer to the nucleus? Okay, you all notice the bond pair is shared between 2 atoms, right? That's why it is clearly a lot further from the nucleus of fluorine. On the other hand, the lone pairs are a lot closer because they don't need to share. They just stick to the nucleus as close as possible. In other words, you can look at it in a relative point of view. Lone pairs are further from the nucleus. Lone pairs are closer to the nucleus. And as a result, if you are closer to each other, that means you face more or less repulsions. More repulsions. So lone pairs are closer to the nucleus, so that's why it faces stronger repulsions. On the other hand, because bond pairs, right, are like in the region in between two atoms, it is technically further from the nucleus. So if you're further away, do you experience stronger or weaker repulsions? Weaker. So bond pairs, in contrast, further from the nucleus, so it ends up experiencing weaker repulsions. So again, right, this is a very simplified way of looking at why lone pairs tend to repel more than bond pairs. And if you have lone pair plus bond pair, it's kind of like a mix of both, that's why it's in the middle. Okay, so I don't want to just ask you guys to memorize. I used to tell people that, but again, it doesn't really work all that well. Try to use this diagram as like a mental image here. Okay, lone pairs are objectively closer to the nucleus compared to the bond pairs. Bond pairs are given out to share, you can see the idea. Okay, you need to stick out your hand to share an electron. Okay, but you don't want to share, you just keep it to yourself, right? So it's closer. It's kind of like that idea as well. Okay, so once we understand this, right, by placing both of these principles together, we can have a variety of shapes of different structures. So guys, what on earth is the point of VSEPR theory? Okay, VSEPR theory seeks to explain one thing: the shape and the bond angle of a molecule. Now, what does this mean, guys? In the previous lesson, when you all draw dot and cross diagrams, like for example, CH4, you just place carbon in the middle and then just surround hydrogens very nicely like this, right? But now, right, we need to actually account for the different shapes. You can't just draw whatever shapes that we want. Okay, CO3 2 minus. You can no longer just place your oxygens in this manner over here. It's a very strict shape that you need to follow. Okay, so as for how we determine that shape, that's when we need to look at the next page. Go over to page 30. This page, please mark it out as a favorite page, because you will need to know every single detail on this page. I'm not just going to ask you guys to memorize. I will tell you guys all the specifics. So come, bear with me. The next 2 pages, I'm going to go very, very specifically into pretty much all the details. Okay, guys. Number 1, I hope you all can navigate the table a little bit with me. There's a column called number of bond pairs and number of lone pairs. Guys, bond pairs, lone pairs add together is called what? What do you call both of them? Electron pairs, as mentioned over here. So you can see that's the initial column. I'm going to start at the easiest. 2 bond pairs, 0 lone pairs. I'll use the example in the notes as well. You will end up with something like this. Look at the central atom. There are clearly 2 bond pairs, right? Okay, since there are no lone pairs to talk about, if you have 2 bond pairs, they want to be as far apart as possible, right? Can you all see the furthest apart is what angle? What's the angle between the 2 bonds? 180, that's the furthest they can go, correct? I mean, if you put one angle like that and one like that, it's not the furthest they can go. The furthest is 180 degrees. Very obviously because 2 bond pairs are going to repel the same. You see that? Same amount of repulsions, no lone pairs over here to interfere. That's why the furthest they can go apart is 180. Again, the further you are, the more stable. They want to have as little repulsions as they can. This is a very easy idea. The shape in this case is very easy to remember as well because linear just means straight line. So I'm sure it's no problem. You can also think of it this way. You can take 360 degrees, divide by 2. Why can you just divide by 2? Because again, bond pairs are equally repulsive. Later we'll see a situation that they are not equally repulsive. Okay? I'm going to start changing the numbers up. So guys, take a look. Instead of 2 bond pairs, 0 lone pairs, I have 3 bond pairs. I don't introduce lone pairs yet. Guys, imagine you have 3 bonds. What is the angle they have to be apart of each other? Here, 360 divided by 2, 180, right? How about 3 bonds? 360 divided by 3, you get 120. So you can think of it as a circle cut into 3 pieces. Why are we able to evenly do this? Once again, guys, are they going to be equally repulsive or not equally repulsive? Equal, because they're all bond pairs, right? Okay, they will very nicely adjust themselves into this shape over here. This shape is called trigonal planar. Now, I don't want you all to just accept the name. It's a lot of things for me to go through here. And I want you all to kind of label the bond angle as well in the diagram. I know it's not labeled because they say separately. Okay, but it's good to label. Now guys, let's explain the name. Three, right? Okay, that was simple. You're gonna just memorize that. What's planar? Okay, come. Any idea what planar means? Any clue? Okay, so guys, planar just means a plane, right? Imagine this, I take a piece of paper, it's flat, right? If I were to take this molecule and slap it onto this paper, what do you expect to see? It's gonna be flat as well. It's gonna be on the same plane as this paper, basically. So if I slap the molecule here, it's flat, nothing is protruding out or protruding anywhere. Okay? So in other words, planar means two-dimensional. Okay, go and take note of that. It's very important now. You all need to know what is a planar molecule, which is 2D, and what's the opposite of planar? Non-planar. Okay, later I'll go through. Non-planar just means 3D. That means if I were to take a 3D molecule and then slap it onto this flat paper, what would you see? Will it be completely flat? No, there'll be stuff sticking out basically. Okay, Ken? Okay, now let's make things a bit more complicated. Right. Instead of 3 bond pairs, 0 lone pairs, I'm gonna have 1 lone pair and 2 bond pairs. At the end of the day, they both add up to 3 electron pairs, right? Okay, how does this work? I'm gonna replace the bond on top with a lone pair. I'll borrow the example from the notes. You see, the only difference is I replace the top. Guys, from here, can you see what's the bond angle? Okay, let's just mention first, the shape here is bent because literally it's bending. Okay, now you notice something. The bond angle here is 120 degrees because you can just take 360 divided by 3. Is there a way you can evenly divide this? Because guys, lone pair and bond pair, do they repel equally? No. So that's why over here, there's no way to calculate this. Scientists had to actually use some sort of technology to measure that bond angle. So the bond angle here is 180 degrees. It is a little bit of a weird example. Again, why is it weird? Because guys, I hope you all notice something. This lone pair is stronger or weaker in terms of repulsions. Lone pair repels more, right? Now you compare it with the first structure I drew. You notice if you have two bond pairs, it's equally repulsive. So the angle on top and angle at the bottom is the same, 180. But is the angle on top and the bottom is the same? Is it the same? No. Because can you all see here, let me erase the bond angle first. What is the bond angle on top? Sorry, not bond angle. What is the repulsion over here? Which one? This is a lone pair repelling with a bond pair. Agree? And bottom here is bond pair repelling with a bond pair. Who's stronger? The top or the bottom? As long as the lone pair that's stronger, right? So can you see, if the top repels more, it's going to squeeze the bottom down a little bit. Yeah, okay, visualize your head. Okay, you need to be able to visualize how the shape comes about. Here, they are equal, so very nice. But because here on top, there's more force, right? It's just going to squeeze it downwards. Of course, you don't need to explain this, thankfully. Just make sure you can rationalize this. Okay? So the top half repel more than the bottom half. That's why it is bent. Angle here, no choice, must memorize 180 degrees. Okay? 2D or 3D? Okay, still 2D. Okay? So bent 2D shape. So far, so good. So things start to get interesting when we introduce lone pairs into the equation. Lone pair, bond pair, no need to know the angle. Okay, our angle, just to clarify, bond angle is between the closest two bonds. Bonds are not lone, okay, between the closest two bonds. The reason why I say the word closest, later I'll explain. Later you see an example. Now it doesn't matter. Okay. This page ultra important because the bonds are there's so little things. The molecules are very small. You flip over to the next page, right? That's where things start to get a bit hectic already. Never mind. We settle this page first. Okay. Any questions, please ask right now before I continue on with the 4 electron pair configuration. Okay, I use this space here. Okay, same thing. Bond pair. and lone pair. Now, instead of 2 or 3, I can go to 4. Okay, slowly increase. If I have 4 bond pairs and no lone pairs, okay guys, if you just look at the numbers here, right, what will you expect the bond angle to be? Okay, which is 360 divided by 4, you get 90, right? 90 just means 1, 2, 3, 4. Hey, very nice, right? 90 degrees apart. They're all equally apart because they're all bond pairs. But if you look at the notes, there's no such thing. There's no such thing as this anymore. If you draw this, is wrong already from now on. Why though? That's because, guys, it's not the best way to minimize repulsions. There's another way it can arrange itself such that you can minimize your repulsions even more. So guys, here what's the angle first? Okay? And as I mentioned, it's not the best. It could be better. What does it mean when I say better? The angle is larger or smaller? It can be even larger. It can be even further apart from each other, and you will have even less repulsions. That's why this does not exist. There's a better way of doing this. How? Now, do you all remember the stupid tripod that Ita keeps using? Okay, think of that tripod. Okay, that one very important here. Because this shape is called tetrahedral. Now, on first glance, it looks weird, right? It looks very odd. How on earth is this better than the previous configuration? The previous configuration is all 90 degrees apart, all equal. But what the hell is this, right? We have here so big, here so small. What's going on? Okay, it's because, guys, tetrahedral is not a 2D shape. Okay, take note. Tetrahedral is a non-planar structure, which means 3D. You cannot look at it as if it's a 2D shape. It's not actually. This is 3D. Why? You probably can't see it right now yet. Okay, but I need you all to imagine my hand over here. Okay, you all know how a tripod looks like, right? It's 3 legs at the bottom. Now, those 3 legs are these 3 guys. You see? And with these 3 legs, the bond on top is just on top like this. So this is actually the best configuration for 4 bonds because the bond angles in this case are 109 degrees. It's higher than 90, so there's even less repulsions than 4. So again, they are very smart. Electrons very smart. They want to be as far apart from each other as possible. And that's what they came up with. Okay? Now, because I think RI, right, they teach this right now in your notes soon. Later you'll see. I want you all to draw another way to show a 3D structure. So just copy this down first. This guy, right, actually looks like this. You might see this shape, or you might see this notation in your notes when you receive them. Draw separately, you don't need to edit the thing. You just draw separately. I will introduce what this notation means now. Okay, usually I introduce this late into J1, but because RJ notes have this, I'm going to teach this now. Okay, so anyways, I'm going to write a legend at the top as well. Okay, it's still a bond, don't worry, but this is to show a 3D structure. The solid line, the black one, is pointing outwards. The dash, the dot, is pointing inwards. We'll explain what this means. Again, keep thinking of that damn tripod, right? Okay, that tripod stand, basically. Okay. Okay, this way of writing it, right, is very nice because it actually shows a 3D shape. Now, this means pointing outwards, right? Can you imagine my 3 fingers here are a tripod stand? Can you see? This line, right, is basically along the whiteboard. Nice. But this is not along the whiteboard. It's pointing outwards towards you guys. Can you see that? Make sure the camera can see also. But this bond is not pointing along the whiteboard. It's pointing into the whiteboard, inwards. Can you see? Okay, so you might want to take out your tripod, right? And then that's how a tetrahedral looks like. The top is just pointing on top. Okay, this is the furthest it can separate from each other at 109 degrees. One of the most common shapes. You must understand how this works. There'll be more 3D shapes coming up. Okay, so hopefully you all can visualize. Okay, very good. The next one I'm going to go over, instead of 4, 0, let me just change the numbers a bit, 3 and 1. Okay, hey guys, by the way, talk about one more thing. Here and here is still 109, by the way. I'm going to write this down also. Because I think, right, it's very hard to get out of that 2D mindset. Come. Over here, it is obviously 109 because this is an obtuse angle. I'm pretty sure you all know obtuse and acute angles, right? This is clearly acute on the 2D standpoint, but it's not. Because if you do this, from here to here, it's actually obtuse. It's just that on the 2D piece of paper, it looks acute. Does that make sense? Okay, try to accept that first. Come to terms with that. Because for 3 and 1, instead of the bond pair on top, I'm going to change it into a lone pair. And guys, the 3 legs at the bottom are still the same tripod 3D legs. So I'm going to draw the same version, go and draw this in also. The 3 people at the bottom here are the tripod stand. Okay, right? What's the bond angle? Okay, wait, shape first, sorry. Shape here is called trigonal. You all know why it's trigonal? Want to make a guess why it's trigonal? 3 what? Trigonal means 3. There are 3 bond pairs now. Okay, so it's called trigonal also. And the next word is called pyramidal. Hey guys, does this look like a pyramid to you? Kind of, right? Okay, yeah, so that's how I come to terms with this kind of names. Okay, Ken? Anyways, bond angle here is what I'm trying to discuss. Okay, but first of all, 2D or 3D? Still the tripod leg, right? Okay, this notation already means it's non-planar. Write all this down. It's 3D shape. Can the camera see? No. Okay. Guys, where is the bond angle? Now you notice here, bond angle can be between any bonds, right? They're all equally spaced apart at 109 degrees. How about here? Can it be here? Can I measure bond angle here? Why cannot? It's literally called bond angle, right? Between 2 bonds. Is this a bond? No, so never ever label your bond angle here. The bond angles you can only label are here and here. And the bond angles here are 107 degrees. A bit different. Later we'll explain why. Or perhaps we can explain right now actually. Why is it smaller than this? Think about it. Why is here at the bottom squeezed smaller compared to the top? What was the repulsion come? This is a lone pair, bond pair repulsion. Whereas up here, that same place is a bond pair, bond pair. Now, can you all see which one exerts more force, more repulsion? At the top here, right? So if it exerts more force, it's just going to squeeze the bottom smaller. That's why it's smaller. Label all these things because the notes are very empty. Okay, you cannot learn this with an empty set of notes. Okay, all these annotations must be in. No space. Okay, never mind. Okay, all good so far. All right, I draw the last one, which is 2, 2. I draw here. Okay. Now, so instead of this, now we have 2 bond pairs, 2 lone pairs. The classic example is water. Okay, so 2 lone pairs, 2 bond pairs. Now, what shape is this? Have we seen this before? What's it called? Okay, it's a bend shape. Okay, so you will notice, right, there are 2 bend shapes, but the difference is the number of lone pairs and number of bond pairs. Okay, bond pairs are the same. It's the number of lone pairs that are different, correct? So do you expect the bond angle to be the same? No. Okay, in this case, the bond angle, 105. Again, bond angle is between the bonds. Don't go and tell me between the bond and the lone pair. That's not a bond angle, it doesn't make sense. Okay, why is it smaller than the other 2? Okay, so what's the repulsion called? The repulsion here is a lone pair repelling with a lone pair, which is the strongest. So it's going to squeeze the bottom right to the smallest extent. sorry, squeeze the bottom to the most. That's why the angle is the smallest. Okay, bend is, okay, thankfully our bend is still 2D. Okay, so it's the same. Not really related to the other two. Okay. Any issues here? Okay, so this page, ultra important. Okay, so band shape and all that. Okay, I don't want to go over to the next page yet. In fact, I want to touch on the questions. Okay, guys, can you all turn over to page 32? Skip 31 first, I'll come back to that. 32, there are questions regarding whatever we have just learned. Okay, so let's look at the first question. There are two band shapes, but they have different bond angles. Why? Come, the band shapes are literally right next to each other here. Why? Okay, this is lone pair repulsions on top. How about this one? Lone pair, bond pair. Who repels more? So if you repel more, that means you'll be squeezed until it is smaller, right? That's the answer. So how do you explain this? Okay, very quickly, just tell me, right? The bond pair, lone pair repulsions. Water has lone pair repulsions, which are stronger than the lone pair bond pair repulsions in SnCl2. Now guys, you notice how I'm already trying to cut down my answer, which is what I've been telling you guys for the past 2 lessons. To cut down your answer, don't just say this. This is what you all might do. Water has lone pair. SnCl2 has lone pair bond pair. Lone pair is stronger than lone pair bond pair. You see, you're writing too much. I even, it's such a pain to talk about it. Right, okay, so this is what you can do. Okay, I'll give you like suggestions here to cut down your answer. Once you compare the strength of the repulsions, then just tell me, go straight to water has a smaller bond angle. It's quite easy to explain. Okay, lone pair, bond pair, and compare the strength and finish. Okay, highlight the keywords, right? And I'm pretty sure, right, with this, you all can try the next question already. Okay. Okay, same exact type of question, same exact way of explaining. Okay. Okay, all good. Okay, so that's it. What's the answer to this question? Why is this slightly smaller than this one? Here we mentioned there's lone pair, bond pair repulsions. This one, bond pair. Which one stronger? The one at the bottom, right? This is stronger, so it's going to squeeze slightly smaller. Yeah, that same exact thing. Okay, all good. So with that said, let's come back to page 31. And I want to go through the slightly larger compounds. Now, unfortunately, there's no anything that we can skip here. Okay, all of them are equally important. So bear with me first. I know this is a little bit painful to go through. Okay, but slowly. Okay, let's look at the 5 electron pair group first. Okay, 5 electron pairs. The first one is really very important. 5, 0. They love testing this shape. Okay, but I want you all to color code this. Okay, later I'll change it up a bit. 5 bond pairs. I'm going to draw 3 of them in red. And the other 2 in blue. Because from the notes, a lot of people see this and then they just go, oh, it's a 2D shape. All 5 bonds are flat. No, that's wrong. Okay, because let's explain slowly. Number 1, this guy's name is called trigonal bipyramidal. Say again, trigonal bipyramidal. This one you just need to memorize. Okay, nothing here looks like a pyramid. Actually, kind of does, but I can't explain. That one is visualizing. Okay, never mind. What I'm going to do here is I want you all to look at the bond angle. What did they print there in the notes? They use the words axial and equatorial. Why is it so freaking confusing, right? Okay, come. Now, can you all tell me, right, what's equatorial? What does it remind you of, this word? Equatorial comes from the word equator. What does an equator mean? Like, you all know what equator is on Earth? Okay, so we're going to use Earth as a visual diagram. Earth looks like this. Where's the equator? Around this part, right? Okay, do you all notice? Equator literally means the flat part. That's what I need you all to visualize. These 3 red color bonds are the equatorial plane. They're flat like this. Okay, I'm going to use markers to show you all this. From here, you all will look at the 3 bonds like that. You see that? But it's actually not like this. Can the cameras? Okay. It's not like this. It's like this. I do again. It's not like this. It's like this, flat. From your perspective. Okay? Meaning to say, if you all think of the flatness, right, it's basically lying on the equator. So come look at my Earth. My Earth, right, flat here. Basically, these are the 3 bonds. Okay? I hope you all can visualize. Doing my best to help you all visualize here. It's not like this, it's like this. Okay? So guys, I color code this equatorial. Can you all just focus on the 3 bonds here? Can you all tell me what the bond angle is? What shape does it remind you of, by the way? 3 bonds just, equally far apart. 3 bonds splitting the circle in. It's trigonal planar, right? Trigonal planar, what's the bond angle? 120. So there's like 2 parts to this molecule. It's a bit interesting here. Okay, equatorial is 120 degrees because flat. Okay, 360 divided by 3. In other words, now I'm just going to change this a bit. You all notice these 3 bonds is actually flat, right? This bond, okay, look at the bond here. This bond, is it pointing inwards or outwards? Visualize. Look at the Earth if you want. This bond, inwards. This one, outwards. You still can't see it. Let me just use my markers again. It's not like this. It's like this. Can you see? My blue marker is pointing out towards you. My red marker is pointing into the whiteboard. The black marker, this one, this guy here, is still the same. I mean, twist from here to here is the same one, right? Visualize like that. This is how you draw it with the 3D notation. Yeah, I think you all can understand the 3D notation. That's why I'm teaching you all this now. Okay. Next, what do you think axial refers to? Now on Earth, what's at the axial? What was that on Earth? It's the North Pole and South Pole, right? Can you see that? Okay, so North Pole and South Pole is called the axial plane. It's like axis, I guess. That's where the word comes from. Guys, can I ask you all, what is the bond angle for the axial plane? Just try it. What do you think is the bond angle for the axial plane? The 2 blue color bonds, North Pole, South Pole. Okay, you will say it's 180. I won't fault you all for that because I did say between the 2 blue color bonds, right? But guys, bond angle, come back to this, is between the closest 2 bonds. The blue bonds here, are they the 2 closest bonds to each other? No. In fact, where are the closest bonds? The blue followed by one of the reds. Can see that? Between the blue and the reds, what are the bond angle? What's the bond angle here? 90. Can you see? No matter what, the blue and the red is 90, 90, 90. Okay, I hope you all can see. My drawing them bad, but I really hope it gets the point across. It's all 90. Don't look at it as an acute angle. Wrong. This is not an acute angle. It's 90. That's why axial is 90 degrees. Not because it is with the other south pole, but it's because it has to be the closest two bonds. Okay, unfortunately, we have to follow this closest two bonds. Okay, that's why it's 90 degrees. All good so far. Your exam, okay, if they ask you about the bond angle, right, you can give me either. You want to give me both, even better. You want to specify which one is which, the best. Okay, good. So earth and energy done. All good. Okay, next, let's move on. Okay, the rest are kind of like modifications of the first one. So let's proceed over very quickly. Okay, I can reduce to 4-1. Okay. So 4-1, right? I'm just going to change this into a lone pair. Okay, so I'm going to use the color coding again. Okay, everything's the same. This is a lone pair now. And then the blue color is just your north pole and south pole. Quick question, guys. 2D or 3D? Okay, just like the first one, it's all 3D, right? Okay, go and write this down. Trigonal bipyramidal 3D. Now, this shape is called seesaw 3D. Perhaps can y'all try to figure out why it's a seesaw? Y'all try to exercise your visualization skills. And see what's a seesaw. Maybe if you turn your head like that, kind of looks like a seesaw, right? Yeah. Okay, I don't know why they call it that way. They ran out of ideas, huh? Okay, but anyways, 3D shape. It's the same as the top, it's just that this one becomes a low pad. That's it. Hey guys, the axial and equatorial still exists here, and it is the same. It is the same as before. Okay, refer to that. Okay, next 3-2. 3-2, okay, the shape starts to get a little bit different already. Okay, I'm just going to use an example there. So not much for me to explain, honestly. This is a T shape. Everyone can figure out why it's a T shape, right? Okay, so T shape, you have to make a smart guess what a bond angle is. T, letter T, what number? Letter T, 90 degrees, right? That's it. Okay, so this is literally 90 degrees. And yeah, this is the most stable configuration that it finds itself in. It's the most stable you can find. Okay, anyways, T shape is surprisingly a 2D shape. That's why there's no weird, funny notations. Okay, T shape is 2D. Okay, this is quite simple actually. Okay, last one is a little bit weird also. Okay, but anyways, it's 2, 3. 2 bond pairs, 3 lone pairs. The one that you use in the notes is this. Okay. 3 lone pairs, so 1, 2, 3. I know there's an overall minus charge. Okay, but you can draw that inside also. Oh my god, this guy. Okay, anyways, this is clearly what shape? Straight line. So it is linear 2D. Yes, linear means straight line. 2D angle is what? Now remember, bond angle between the bond and the bond. Don't go and tell me the lone pair. Okay, bond and bond 180 degrees. Very easy. And perhaps I can give you guys a bit more insight, right, to why this. I ask you a question now. What's the repulsion here? Not bond angle, the repulsion type. Okay, lone pair, bond pair. Can you all tell me what's the repulsion type here? Lone pair. Who is stronger? Okay, lone pair is stronger. So shouldn't this have more repulsive force and bend it like that? Agree first? Does that make sense? Shouldn't this side have more repulsive force? Why is it equal? Okay, I never really see them ask this question before, but I started to realize this recently. Never really thought about it as well. One way you can explain is this. If you notice, maybe here's lone pair, lone pair, bond pair. This side is also a lone pair, bond pair. Maybe for some miraculous reason, the lone pair, bond pair, lone pair, bond pair add together is equally as strong as the lone pair repulsions. That could be a reason. Again, we're not really required to answer that. I never see a question like this before. But to really stimulate your thinking, I'm like, why is it like that? Why is it equal? I thought equal just means bond pair settle. Oh, but a bunch of lone pairs over here as well. Okay, but again, not much to discuss here. It's not that big of a deal. Okay, can? Yeah, okay, so that's 5. Okay, generally, 5 electron pairs is probably the most difficult one. Okay, you might need to spend quite a bit of time on this. But what's more important, I would say, is 6 electron pairs. Okay, any questions so far? Oh, the bracket is because this compound is called IF2 minus. Remember in dot and cross diagrams? Dot and cross diagrams, you need to bracket the whole thing and have the negative charge as well. It's just that this compound is an anion, not a normal compound like the rest. Yeah. Okay. Okay, moving on to 6. I know this is a drag, okay, but try to make it as, okay, you need to think as much as possible, visualize as much as possible so that you don't get bored from this. Okay, anyways, next, bond pair, lone pair. Now 6 is surprisingly easy. Yeah, okay, there's less stuff as well. Okay, so guys, take a look. Bond pair, lone pair, you have 6, 0. Okay, actually, this is the best. Okay, it's not very easy to memorize because I need you all to visualize this again. Remember the axial and equator? Same thing. SF6. The 4 bonds over here look like that. And then I'm going to use blue again to represent the North Pole and the South Pole. I'm going to use the Earth analogy again. Okay. Is the Earth? On my Earth, I have an equator. Guys, just now the equator was how many bonds? 3 bonds, right? But now my equator has 4. How do you arrange 4 on the flat plane? 90 degrees. Now, how about just now? You all remember tetrahedral? How come that one was not 90? Why was that 109? Okay, you notice, guys, this is flat, agree? So you cannot go beyond 90. Here is flat, so that's why you can have 90 degrees apart for all of them. But just now you had the 3-dimensional version. That one you can go even further than 90. But now we are restricted to a flat plane. Just now we were not restricted. Can see that? So that's why now the furthest you can go is 90 and not the stupid 109 tripod shit that we discussed earlier. Can see our restrictions now? Okay, because of that, okay, let's take a look. Our top and bottom is our North Pole and South Pole. Okay, our red color is what angle again? Sorry. 90. Our North Pole to the closest bond is what angle? The North Pole and South Pole is perpendicular to the equator, right? So it's also 90. That's why all in all, the bond angle here is 90. There's no equatorial axial, but there is okay, there's an axial and equatorial plane, but everything is 90. That's why they never specify. Okay, so this is called octahedral. Just remember the name, 90 degrees. Remember, equator plus North Pole, South Pole, same as before. Okay. 5-1 is not that important. Because for 5-1, right, we have something very similar, but instead of the bottom F, I'm going to remove, okay, hear me out, I'm going to remove the South Pole. Okay. I am going to remove the South Pole. The North Pole is still there. The South Pole has been replaced with a lone pair. Guys, what's the bond angle? Okay, it's still 90. Okay, it's the furthest they can go from each other. Because even if you replace the South Pole with a lone pair over here, right, you can't repel this out of the plane, no. Okay, so it's not affected. Okay. This guy is called square pyramidal. Honestly, guys, when you see the word square, Just put 90 degrees. It's very easy, right? Okay, square 90 degrees. Finish. I don't know why it's a square also lah. Okay, I guess I could see why. Because the 4 red color bonds is technically a square. Because 90 degrees. Yeah. Okay. Now, the last one. There's not much over here, only one more. 4-2. Okay, you notice, here, I got both North Pole and South Pole. Here, I only have North Pole. Here, I don't even have any poles. Okay, okay, so anyways, here, right, I have no poles, but only my equator. Kind of looks like a spider, I guess. Okay, so look at my Earth again. No more North Pole. Okay, one question, 2D or 3D? I only have my equator, so it is a 2D shape. That's why this guy is called, very common one, by the way, very common, 4-2. It's called square planar. Planar, planar means 2D. Square, you see the word square, just give me 90 degrees. Everything is 90 degrees. That's why it's much easier to start with this. Guys, square pyramidal, 2D or 3D? Okay, because you have a freaking North Pole sticking out of your equator, right? Octahedral, 2D or 3D? 3D also. And we don't use the word 2D or 3D in exam, we use the words planar and non-planar. Okay? But 2D, 3D is really will help you all understand what it means first. Okay, I know it's a lot of shit, I know it's a lot of shapes. That one we need to slowly get over time. That's why we have a page full of practices after this. Okay? Okay, once you're done with this, we're going to do some exercises on page 33. Okay? On page 33, okay, I tell you what to do first. Today, we're going to learn how to draw all the structures, including all the shapes and bond angles. Okay, and the way to do that, guys, to determine the final shape and bond angle, you need to first draw the dot and cross diagram. If you can't draw dot and cross, you don't even need to talk about anything else. Okay, so I'm going to go over one question with you guys, then the rest you can try yourself. Let's try part 1, SO3. Yeah, okay, SO3. Just draw the dot and cross first very quickly. See whether you can recall whatever we discussed. All right. Okay, so again now guys, when you draw dot and cross, you don't have to bother about any shape. Don't have to care. So I think some of you all actually going to try the shapes inside, right? Okay, yeah, try not to first, because we haven't confirmed the shapes. So for SO3, just arrange whatever that you will do first, like this. Okay, how many bonds can oxygen form? 2. Just do a double bond for everything. Fill in the rest, double bond, fill in the rest, double bond, fill in the rest. Anything else that I need to fill in on sulfur? Central atom, do I need to do anything more? No. Yeah, okay, so guys, Once you're done with dot and cross, can you all tell me? You must go and count the number of bond pairs and lone pairs. How many bond pairs and how many lone pairs do I have? Come tell me. After you count. Okay, on the central atom, by the way, we've been discussing center. Only look at your sulfur, don't look at anything else. Okay. Okay, so how many bond pairs and lone pairs are there on sulfur, the center atom? Any clues? Okay, so you all will say that there are 1, 2, 3, 4, 5, 6 bond pairs. How many lone pairs? All 6 of sulfur's valence are already used in bonding, right? So there's nothing that are lone pairs. However, you cannot tell me 6 bond pairs and 0 lone pairs. In fact, over here, there are only 3 bond pairs, 0 lone pairs. And that's where I need you all to write this down. Okay? Double and triple bonds are still considered as one bond pair. I'll explain why. So you only have 3 double bonds, so it's 3 bond pairs only. The reason why is because, guys, are you splitting the double bond? Are they going to repel from each other? No, right? Double bond is a unit. They're not going to repel because they don't like each other, then become 2 single bonds. How does that make sense? Right? So a double bond is considered as 1 unit. Same thing for triple bond. A triple bond can't just split into 3 single bonds, you know. That never happens. So it's 3 bond pairs. Okay? Last but not least, when you identify the correct number of bond pairs and lone pairs, that's when you can tell me what the shape and the bond angle of the structure looks like. So guys, can you tell me what the shape and bond angle is for 3 and 0? Okay. Okay, trigonal because the 3 bond pairs, no lone pairs, so they all divide equally, right? Trigonal planar is what bond angle? 120, all 3 bonds split evenly. So these are the steps that you need to take into account for. I'm going to show you all the mark allocation also. But then you must draw the final structure very nicely. Trigonal planar shape, as you can see, like this. If you want to label your bond angle here, go ahead. If you don't, it doesn't really matter. As long as you write it somewhere in your answer. Guys, notice the difference between dot and cross and the full structure is that you do not need to show me the lone pairs on the side atoms. And also, the full structure need to have the nice shape. Dot and cross don't need to care about shape. So I show you the mark allocation. You must have all this in your answer. Number 1, the shape. Number 2, bond angle. Number 3, the final structure. 3-mark question. Yes, it can be a 3-mark question. With that said, I want you guys to try the rest. Part 2 and part 3 are very fast. Perhaps you do part 2 and part 3 first. Okay, so repeat this entire process for the rest. Yeah, write down the answers for part 2 and part 3. They are very, very easy structures. Okay, so for CH4, classic tetrahedral shape. Eventually, when you all get very good at this, you don't need to draw the dot and cross diagrams. Okay, of course, for the more complicated structures, yes. Okay, now this is your tetrahedral shape, and I need to see your bond angle, 109 degrees. That's all that's required for this question. Now, if you want to draw the 3D version, even better, but if you don't, it's fine. It's not a requirement. Okay? Carbon dioxide, very simple. It is a linear shape with 180 degrees. Anyone need me to go through this? No, 2 bond pairs. Okay, keep in mind, 2 bond pairs only, not 4. Okay, continue with the rest, and then once we finish with this, right, okay, you can take a break. Okay, part 4, part 5, and part 6, and then we can chill. Okay. You're going to slowly write some of the answers on the board. In XEF4, I will draw the dot and cross as well. Okay, the dot and cross very messy for XEF4, but no worries. Okay. Okay, you should get 4 bond pairs, 2 lone pairs for XEF4. Square planar. Square planar, you see a fat square there is 90 degrees. Okay, then from there, they can draw the nice little structure. But pay attention to this, your central atom must have the lone pairs also. Only the central atom must show lone pairs. The rest, fluorines, no. Side atoms, no. Okay? Again, you want to draw the 3D version with the notation, go ahead. Right? ICl3. Dot across, I need to see the lone pairs on everywhere. Okay, 3 bond pairs, 2 lone pairs, E shape, 90 degrees. Okay, when you draw the structure, only the lone pairs of the central atom matters. Okay, so that's how you present your answer very nicely. Okay, SO2, last one. Once you're done, you can check the answers on the board. Right? Okay, very good practice coming in now. Anyone need to clarify anything? Okay, so this one's a tedious process, I know. So the entirety of the last lesson is just to master the dot and cross first. Now we add on so many layers to it. Okay, all that just for all these structures, basically. Okay, not easy to learn how to draw these structures clearly, but now we have basically completed that. Any questions? Let's take a break first. That was a lot. Okay, so you know, chill first. Later we go over 2 more rather short concepts and then we'll finish for today. Right? This guy, all right. All right, okay, the next 2 stuff that we're going to cover, one of which is electronegativity. We actually covered a bit of this already. Yeah? So not much left. Intermediate bonding also not that much. Okay, so electronegativity, let's look at the pure definition first. Okay, it's the tendency of an atom to attract a covalent bond. Okay, I repeat, it's a tendency of an atom to attract a covalent bond towards itself. So as I mentioned maybe last lesson, we discussed electronegativity as a tug-of-war battle. In a covalent bond, for example, we have hydrogen and fluorine. There is one bond of electrons. Do you think this bond is directly in the middle? No. Can you remember what are the 3 most electronegative elements? Okay, FON, right? Okay, the top 3 most electronegative, F being number 1, followed by number 2, number 3, right? So these are the strongest people in tug of war, the strongest contenders. As of here, the keyword is attract. Now, first of all, why can an atom attract a bond of electrons? What allows the atom to attract electrons to itself? The nucleus, because the nucleus contains protons, right? And we are basically just talking about effective nuclear charge. We discussed effective nuclear charge in the previous chapter. In other words, we are attracting these electrons because it has effective nuclear charge. Different atoms have different number of protons, so different attractive power. Makes sense, right? Okay, that's why the electronegativity is different as well. In other words, okay, over here in this example, H and F, where are the electrons closer towards? F. Because clearly, F is way stronger than H. But now, right, since we're properly discussing electronegativity, it may not be enough to just look at FON. Sometimes we don't have these three elements. So we're going to look at how we navigate the periodic table, so that you can compare pretty much anything. Number one, electronegativity increases across a period. Come, let's discuss this. Guys, across a period, how do we justify our answer? Remember, we discussed this in the previous chapter. You go across a period, you must look at effective nuclear charge, right? Because the number of shells remain the same. Okay, that's the factor we discussed. Can you remember what is the formula for effective nuclear charge? Oh no. It's nuclear charge minus shielding effect. Yes. Okay, so across the period, what happens to the nuclear charge? Nuclear charge increase because you have more protons. What happens to shielding? Remains relatively constant because you're adding electrons to the outer shell, not the inner shell. Right? So let's remember all these things again. That's why the effective nuclear charge. Again, I'm going to go over this fast because it's really not the purpose of this portion here. Again, so number of protons increase. Nuclear charge increase. Okay. Shielding effect is relatively constant. Okay, because electrons are added to the outer shell. Now, if you're added to the outer shell, that means the inner shell is not affected. Remember, shielding effect is dependent on the number of inner shell electrons. The more inner shell electrons you have, the stronger the shielding. Okay? Anyways, now you can say that the effective nuclear charge increases. Guys, what's the next relevant concept to discuss? You have a higher effective nuclear charge, that means what? You're slowly linking towards electronegativity. Electronegativity discusses the attractiveness, right? So attractiveness must increase also. Okay, so attractions between nucleus and valence electrons increase. So you can finally conclude that electronegativity increases. Very quickly, again, the keyword here is attractions and everything else, because it's relevant to our definition of electronegativity. Okay? Get this done and over with. I'm just going to quickly proceed over to the next one. Down the group is even easier to explain. It decreases down the group. Can you remember when we come to down the group, right? What is the concept behind this? How do we explain down the group? The number of what shells? Quantum shells. What happens to the number of quantum shells down the group? Increase. So if the number of quantum shells increase, what does that mean? Okay, we don't have to talk about shielding here, but you see, what happened to the valence electrons as the number of shells increase? Okay, so valence electrons further away from the nucleus, so okay, what's the next relevant concept? Okay, further away means, okay, yes. At the end of the day, link back to attraction. So attractions will decrease, attractions between nucleus and valence electrons decrease, electronegativity decrease. Very quickly, okay, don't really want to talk about this all that much. Okay, so far. Next. Okay, very quickly, maybe there's a box there. Okay, we can just draw in the periodic table. And this is how you pretty much navigate it yourself. You go down the group, the electronegativity drops. You go across a period, electronegativity increases. Can you tell me, right, which quadrant of the periodic table has the highest electronegativity? Top right. Okay, very good. And that's where the top right you will find fluorine, oxygen, nitrogen. Anything else you can just compare using the trends. Okay, I also did mention down the group and across the period, the trends must always be same or opposite. Opposite of each other. Doesn't matter electronegativity or whatever. It's always opposite. Can? Okay, with that said, okay, let's move on to something that's actually relevant to our electronegativity. So I erase this up. Okay. So we're going to discuss the concept of polar and non-polar bonds, new terms here. Okay, you see HF again. H and F, the electrons are lying towards F. F is stronger, right? So we do not want to put the line like this because it's super ugly. The line will always be in the center of the two atoms. There's a nicer, prettier way of expressing this. So guys, if F has more electrons, it must have an overall positive or negative charge if there's more electrons. It should have a minus, right? Hydrogen has its electrons stolen away, so if you have less electrons, you should have an overall what charge? Positive. Okay, but guys, do you think it's actually negative and positive? Do you think the electrons are really given to fluorine? No. Fundamentally, it is still being shared, right? So there's this new charge over here called a partial positive and partial negative charge. So let's explain now. It is not actually a positive or negative charge, as no electrons are actually being transferred. At the end of the day, these electrons are still being shared. It's just closer towards fluorine, but it does not belong to fluorine. So we can't actually put full charges because that's not an ionic compound. The only other way we can do this is a partial charge. Okay, these are called partial charges, not actual charges. Okay, the partial, it looks like this. I took music last time, so I know it kind of looks like a musical note. You want to draw as S, right? Also can actually. Okay, just an S if you struggle with this. Can so far. Okay. The next thing we're going to introduce is this. I'm going to draw this arrow. The electrons are going towards F, right? This arrow here represents a dipole moment. It's just a fancy name, right? To say where the electrons are gravitating towards. Guys, there's this small little line here, you can see that. This small line here is to distinguish this between this and the dative bond. Dative bond is arrow, dipole moment is arrow with this line to distinguish. Okay, so it's just a notation, let's just follow it. Now, let's move on to, okay, before that, guys, a bond that has an electronegativity difference, like HF, is called a polar bond. Got it? Now, the opposite of polar is non-polar. Can you all tell me what do you think a non-polar bond means? No electronegativity difference. Can you all tell me in what kind of bond will you see no difference in En? If the atoms are the same. For example, a HH, Cl, Cl. Guys, they both have the same strength. There's no difference. But take note of one more. CH. Guys, this CH here is considered non-polar. Now, even though they are different, the reason why is because the electronegativity is super similar. So similar to the point where it's considered non-polar. You see that? Okay. Take note from now on. Non-polar, don't have to do all this notation because it's nothing to do. Okay, can. Now, at the bottom of page 36, let's take a look. We have learned polar bonds, but what do we actually use it for? We want to discuss molecules. Because at the end of the day, most items are molecules, not just singular bonds. Okay, but to have a polar molecule, very simply, you also must have polar bonds, right? No shit. But at the same time, this is the important part. Okay, the dipole, there must be an overall dipole moment. To give you guys a bit of a clue here, basically, they cannot cancel out. Okay? They cannot cancel out. What do I mean by that? Okay, you won't understand until we look at some examples. So let's look at page 37 together. Guys, on page 37, there are some examples. Let's look at part 1 together. We have water. So guys, for water, right, I need you all to first draw the structure of water for me. Now, when I say structure, I don't mean dot and cross. I mean the structure, including the shapes that we have learned from VSEPR. The shapes are integral to what we're going to do right now. So you see, everything is building on top of each other. Keeps on going. Okay? Okay, and we have water, right? We need to know the shape and all that. Okay, what's the shape of water? Oh, no. It's actually a band shape. Now, guys, from now on, please take note. Water is this shape and just memorize this structure. Lone pair must be inside, remember? Okay, because of your two lone pairs, okay, you have two bond pairs, two lone pairs, you will get a band shape like this guy. Makes sense? Okay, water is never linear. Okay, anyways, let's discuss whether this molecule is polar or not. Guys, is there a difference in electronegativity? O and H, who is more electronegative? O, right? O is the number 2. So give him a partial negative. H is a partial positive, right? Where is the dipole moment pointing from? From where to where? Where's the arrow pointing? From O to H or from H to O? Okay, good. Because the electrons are going towards oxygen. You repeat the same thing for the other side. So you should know your structure could look something like this, right? Can you see that? Yeah. Looking at this, guys, is there an overall dipole moment? Can I ask you all, look at the arrows. Overall, where's the arrows pointing towards? It's like upwards, right? Is there any cancellation by the arrows? No, they're both pointing up. So there is an overall dipole. So water is a polar molecule. What I need you all to do now is to do the same thing. Draw the structure of CH3F, including the correct shape, by the way, and ask yourself whether it's polar or not. You give that a try also. In fact, you can just try for the rest. Okay, so your CH3F is a tetrahedral shape. Now, it doesn't matter where you place the F because you have to understand they're all pointing in 4 equal directions. 3D, right? 3D for all 4 directions. Now, guys, is there a polar bond here? CH, is it? Okay, it's CF, good. Okay, so for CF, we have a partial negative on F, partial positive on C. F has stolen the electrons, right? Okay, dipole moment is pointing from C to F. Overall, does the molecule have a dipole? Yes. Okay, so this is a polar molecule. Now, some structures that you need to memorize some molecules where you need to memorize the structures are like CH4, water, and carbon dioxide, even ammonia as well, NH3. Never mind, okay, eventually we'll know. Carbon dioxide we have done just now already is a linear shape, correct? Okay, but the dipole is where? It is from O to C or C to O. Okay, it's from C to O, so we have partial negative, positive, negative. The electrons are going towards O, the dipole, sorry. Is there an overall dipole? No. Can you all see, right? This is an example of the dipoles cancelling each other out. So even though carbon dioxide has polar bonds, it doesn't have an overall dipole. So is this polar? No. It is a non-polar molecule. You take note of that. Polar bonds but non-polar molecule because it cancels each other out. So the shape of it plays a part as well. Last but not least, CCl4. What's the shape of this guy? Okay, CCl4. Okay, you can try. What's the shape of CCl4? Okay, tetrahedral, because all 4 bonds the same. Let's go here. Is there a dipole moment in this case? Who is more electronegative, C or Cl? Okay, yes, Cl. Okay, Cl is like very far to the right of the periodic table. So in other words, we have partial charges everywhere. We have dipole moments pointing all towards Cl. So how then? Is it an overall polar molecule? Okay, why not? Upwards? No, it's actually not pointing anywhere. Overall. Okay, notice all of them have the same dipole, right? Okay, and all of them are pointing in all directions. So can you see it's cancelling each other out in every single direction? Now, why is this tricky? It's because a lot of people still are stuck to the idea that these 3 arrows are pointing down and there's only one pointing up. So overall, it is pointing down, right? No. Again, this is a 3D structure. It's pointing in all 4 directions. Just remember the tripod shape, right? It's all 3 directions here and then upwards. So it cancels out everywhere. So the tricky thing is CCl4, please make a note to yourself. Okay, CCl4 is actually non-polar. And let's explain why. Okay, there's a bit of space left. For this question, it might ask you to explain. It's because CCl4 is tetrahedral. You must specify the shape. This all happens because of the shape. Okay, thus the dipole moment of CCl cancels out in all 4 directions. So if it cancels each other out, okay, there is no overall dipole. Highlight the keyword here being tetrahedral, cancel out in all directions. That's basically the main reason why it just doesn't, it doesn't do all this. Okay, it's not polar. Okay, the interesting part about tetrahedral is this one. It cancels each other out. All okay with this? Okay, so basically we have taken all the shapes that we've learned from VSEPR theory, and then now we apply electronegativity to it. So on top of it, there's another layer, right? Okay, so any questions so far? Okay, finally, we're going to take a look at the very last thing. Okay, the very, very last thing for today is intermediate bonding. Not very long, okay, but okay, let's talk about it. Very interesting idea here. Okay, so to introduce intermediate bonding, just go over the page 38. Now, first thing is this. Ionic bonds. It involves the transfer of electrons. Covalent bonds is for the what? Sharing. Okay, so you all notice, right? It is 2 opposite ends of the spectrum, sharing and transferring. Now we all know that, right? However, in reality, it is not so black and white. There's this thing called intermediate bonds, in which you can already imagine it is a mixture of both. You have both sharing and transferring happening at the same time. In fact, you should now acknowledge that most compounds, right, are actually in between that of ionic and covalent. It's kind of like a spectrum. We are mostly in the middle of this spectrum here. Nothing is ever 100% purely ionic. Nothing is ever purely covalent. We'll look at some examples why. As of now, it looks like, what? How's that possible? I thought sharing means sharing, transferring means the opposite. How do you have both? A mixture of both, right? Okay, so let's kind of use like an analogy to help us with this. Okay, let's draw this little diagram. Now, in transferring of electrons, you have a positive and negative. Cation, anion is the transferring of electrons, right? Okay, fair enough. Okay, then what about sharing? How do you form covalent bonds again? Overlapping of orbitals. Okay, so imagine you have these 2 orbitals here. They overlap, and that right there, the overlap region, is the covalent bond. Sharing, literally. Okay, so how does intermediate look like? Okay, perhaps an analogy would be this. Guys, you want to imagine a plus and minus is like platonic friendship between the guy and the girl. Okay, nothing going on between them. The only difference is that they are both of opposite genders, right? Cations, anions, purely platonic, nothing is happening. On the other end of the spectrum, a guy and a girl could be a couple, right? And that's when it's kind of like everything is being shared. What's yours is mine, what's mine is yours, that kind of idea. Then what on earth is an intermediate bond? Intermediate bonding is kind of like a situationship. Have you ever seen this word before? You all know what this word means? I didn't know what this word means until recently. But basically what it means is this. Usually in real life, it's not as simple as friends and relationships, romantic relationships. A lot of the times, there's always this stage in between where you kind of like this person, he probably likes you as well, but you guys never declare anything, right? You never really say your true feelings. So that's mostly how things happen. It's kind of like the intermediary stage between friendship and relationship, right? So how does this work in this context? Now guys, The first scenario that this can happen is this. Fundamentally, we have an ionic bond, but it has some covalent characteristics. Yeah, say again. Okay. Fundamentally, it is about transferring of electrons. It starts off platonic, but then it starts to have a little bit of sharing involved. Maybe there's a bit of flirtatious actions going on, right? Okay, that's when you'll be kind of questioning yourself, what's this person's intention? It may be a little bit of the Richard scenario. Okay, but never mind, let's not bring it into the picture. Anyway, it's ionic bonds with covalent character. So imagine this, guys. I have an ion with a 3+ charge. Wow, very attractive, right? Now imagine now the guy is very attractive to you, okay, or girl. That's okay. Nowadays very complicated. Imagine this, okay? The guy is very attractive. And then what will you do? Are you more inclined to flirt with him? Probably, right? Okay, so platonic friendship, screw that. Okay, there is a chance where you'll be kind of attracted to him as well, right? So look at the anion. It's not 100% separate from each other. This region here, this weird looking region here, is where the cation is so attractive to the point where you can pull a little bit of the anion towards him. This right here is the sharing of electrons. It is pulling it towards the center in order to share. Remember, to share, you must be in the middle region between the two atoms. This right here is kind of like the cation attracting the anion towards himself. Again, why is he able to do this? Because he's very attractive. You can see that? Okay. So that's a situation in which it's an ion, but there's a bit of sharing involved. So ionic with a bit of covalent character. Okay, that's usually how situationships arise. Maybe the person is really very attractive. You're very, very attracted to this person. Okay, next. I want you to compare to another scenario. Imagine the guy, right? Maybe not super attractive, so maybe 2+. Guys, if the guy not very attractive, right? Are you as willing to flirt with this person? You're not going to be as willing to flirt with him, right? So in other words, just like this cation, he isn't very attractive. Oh, my drawing really horrid. Okay, he's not as attractive. So maybe the pulling power not very strong. It's only a little bit of pulling involved. In other words, as you can see here, you compare it to what we saw just now. There is less sharing. Why? Because the cation cannot exactly have that enough attractiveness to pull the anion towards him. Let me draw this again. My God, who's horrid. Okay, so okay, maybe something like this instead. Okay, as you can see, the region of sharing is not as much. Compared to this guy, there's a lot more sharing. So do you all see, right? The chances of you trying to flirt with this guy depends on how attractive he is. Same thing here. The ability, the attractiveness of the cation will affect how much it attracts the anion. So that's the idea here. We're going to discuss about charge density. Charge density of an ion, we've learned charge density before. Can you remember what charge density is? Okay, proportional to charge over, not mass, ionic radius. Yes. We're going to use that to explain again. But imagine this, guys. The higher the charge density, so this is the explanation, the more attractive he is, right? Basically, the higher the polarizing power. Polarize means this, guys. Okay, I introduced a new word to you. Polarize means to attract, to pull that anion towards yourself. That's what polarize is. This action of making the pulling. So new words, new everything. Okay, the cation will polarize the electron cloud of the anion to a larger extent. Okay, so let's read through these sentences again. The more attractive you are, which is your 3+, the more you're able to pull the electron cloud towards yourself. Okay? You must look at this. The word pull is not used. We use the word polarize. Polarize the electron cloud. Now, guys, you cannot polarize anions. You must polarize the electron cloud. Whatever all these little circles, all these weird shapes that you see here, this outline is known as an electron cloud. Basically, it is a region where you can see all the electrons now. Okay? You pull the electron cloud, which is this outline here, of the anion more to a larger extent. Larger extent. Does this make sense first? Guys, is there more sharing or less sharing if you manage to pull more? More sharing. Okay, so the degree of electron sharing is higher. And guys, if you have more sharing, that means what? More covalent character or less covalent character? More. It's a very interesting idea, right? Nothing is ever fully ionic, nothing is ever fully covalent. Because in situations like these, if the cation is super attractive, there is a high chance of sharing of electrons as well. How? Because it just pulls the electron cloud towards it. You pull closer, there's a bit of sharing involved. Okay? So the first factor that we have just discussed, guys, is the cation's attractiveness. The cation's charge density. You can see that. But it's not always just about the cation, right? Sometimes the anion itself could be at play. Okay, so let's look at the other factor. You can turn over to the next page, which is page 39. The anion also affects, let me write it over here now. For the anion, we look at its ionic radius. Let's explain why. Guys, the larger the ionic radius of the anion, what happens? Do you think it's going to be more easily pulled or less easily pulled? Think about it. Okay, slowly up. The larger the ionic radius is further away from the nucleus, right? Okay, so let's write it down. Larger the ionic radius, valence electrons are further from the nucleus. Guys, if you're further from the nucleus, are you going to be more easily polarized or less easily polarized? More. Polarized means pull, start to transition toward polarized. Because you're further away, you're less attracted. So, if valence electrons are less attracted to the nucleus, okay, thus the electron cloud of the anion is more easily polarized by the cation. Okay, I know there's a lot of words here. Okay, so let's summarize. The larger you are further, so you're less attracted. If you're less attracted, means the electron cloud is more easily polarized. Again, I must use the word electron cloud because you can't just say anion. This little outline here stands for electron cloud. So if you're more easily polarized, that means what? More sharing or less sharing? You're going to reuse this sentence. Degree of sharing is higher, you end up with more covalent character. So once again, for cation, we look at charge density. For anion, we look at ionic radius. You may be asking me, why is it so different? Why is one charge density the other ionic radius? Because remember, guys, cation is the one doing the attracting. Okay, I say cation is trying to attract. It's like guys like to try to attract girls, right? On the other hand, anions are like girls. Girls rarely hit on guys, right? Girls are usually the one getting attracted towards these guys who hit on them. It's like the same idea here. Okay, so it cannot be charge density for both. Just imagine they're both trying to attract each other. That's not how it works in real life also. Okay, it's only guys usually trying to attract girls. That's usually how it works. Okay, so just using that as an example, okay, I want you to draw this diagram inside as well to really see. You look at a fat chunk of words here, right? You're just going to get blurred after a while. Okay, so this is to help you see the difference and so far. Okay, so that's that. Next, there's another scenario, very fast one, this one not much. So I'm going to very quickly go over this. If there's ionic bonds with covalent character, you can bet your ass that there is covalent bonds. Fundamentally, they are covalent with a little bit of ionic properties. Guys, how does this work? And why is this not as important? If you notice, there's no box for this. Why is this not as important, right? Guys, a covalent bond is purely about sharing, right? However, there are some situations where there's a little bit of transferring involved. Let me give you a bond, Cm. Is there any sharing here? Yes, right? It's covalent bonds is all about sharing, but are they shared equally with each other? Why? Because of what concept did we learn earlier? Yes, who's more electronegative? Fluorine is more electronegative than carbon, so the electrons technically goes more towards fluorine. We use this notation, we just learned this notation, right? So you notice, guys, is it 50-50 sharing equal? No. In fact, guys, it's maybe about 70-30 towards fluorine. Fundamentally, they are still being shared, but there's a bit of transferring involved. There's a bit of imbalance going on. The idea about transferring is that it's not fair. Sharing is fair. But nothing is ever just not fair and fair. It's usually a mixture of both. That's another idea you can use. That's why it's not that important, because this is just basically what I covered earlier. Okay, so far. Okay, I know just now we started a little bit late, so we are kind of on time already. Okay, so guys, on page 40, we don't have time to do this question. This is homework. Okay, I need you all to do page 40 next lesson. I'll cover the answer. I really pretty much covered the explanation with you guys. You all just go and explain. I'll see your answers next lesson. Okay, but let me just break down the question a little bit so that you all have an easier time. Now, let's take a look. The first part, it says, deviates more from. Part A, okay, it says deviates more from the ionic model. Part B, deviates more from the theoretical lattice energy. Hey guys, what does ionic model mean? Why do they use such funky words? So, I just start off first. Ionic model means, right, you assume it is 100% ionic. They try to throw in these random ass words to make you all feel confused. But no. Guys, then what does it mean to deviate more from the ionic model? If you deviate more from the ionic model, that means you have, okay, good. You have a higher covalent character. If you have more covalent character, that means you have less ionic, right? It's a spectrum. Less ionic means you deviate more. You're further away from 100% ionic. Maybe only 60% ionic. Can see that? So that's the idea there. Part B is pretty much the same thing. Guys, can you remember what lattice energy is? Lattice energy is to measure what strength, what bond strength? Metallic, ionic. Okay, so remember this, okay? Lattice energy is to measure ionic bond strength. Okay, then what is theoretical lattice energy? The word theoretical implies, in theory, everything is usually perfect, right? So theoretical implies 100%. Lattice energy refers to ionic bonds. So part B is the same thing, 100% ionic bonds, which is clearly not true, guys. Okay, nothing's ever 100% ionic now. Okay. So now you should just use those keywords on top of whatever we just explained today. Can see what I mean here? Okay. You deviate further from ionic means you are more covalent. Something like this. So with this, that I've broken down for you guys. Okay, try this as homework. If there's any questions, you can ask me, but if not, that's the end of the lesson. Okay, quite hefty because of VSEPR. If not, yeah, the rest is just about this. Okay, any questions so far? Yeah, okay, so good. That's it. At least you have any questions. If you don't have, yeah, that's all.
Don't have.
All right. Okay, so rest well, get well as soon as possible. All right, bye.